All right, and good morning, everyone, and wish you all well and healthy. Thank you, President Professor Xu and the Chair, Professor Tang, for your kind invitation. It is my great honor to have this opportunity to present my research here. Today, I'm going to talk about multi-scale modeling of unsaturated soil and numerical applications. This presentation summarizes a few research papers published in recent 10 years. Before I start my presentation, I would like to acknowledge the great contribution from all of the co-authors and also the support from the government. Now let's make a start with background. Unsaturated soil is a soil unsaturated with water. Some of the voids are occupied by water and some of the voids are occupied by air. And the pressure difference between the pore air and the pore water is the suction, and how much the voids occupied by water is to the total voids is called the degree of saturation. So there are two key state variables to describe unsaturated soil. So for saturated soil, we understand the deformation and the failure are in general caused by a change of the external stress, for example, loading. But unsaturated soil can experience distinctive volume change, such as wetting clumps and shear strength change upon the variation of the saturation and the suction, even under unchanged external stress level. So here we have an example widely reported in Australia, the Threadball landslide in 1997. So we can see here. So we can see here, the creep in unsaturated soil initiate the leakage of a waterman, and the leakage caused weight-related deformation, which worsened the leakage further. This process lasts at least for 2 months, and possibly as long as 12 months. So soil become fully saturated and eventually lead to a landslide in the end. So like the Threadball landslides, unsaturated soil is blamed for many geotechnical and geoenvironmental damages and failures, like a creek in the pavement, building, teetering, damage of the retaining wall, failure of the GCL system, and a huge number of slope failures. As we know, the main focus of the soil mechanics in the last century was on saturated soil, and most of the soil mechanical principles were developed for saturated soil as well. However, the variation of the soil moisture due to environment and human activities actually is inventable, and most of the shallow foundations and the buried infrastructure systems are in the unsaturated zone. So they are impacted by soil movement and the stress change related to the wetting and the drying. So our research is focusing on unsaturated soil behavior at different scales. So this presentation will cover the following 3 parts, part 1, part 2, and part 3. In part 1, we will talk about the constitutive modeling at soil element level, which is regarded as the fundamental of unsaturated soil mechanics. And in part 2, we will scale up to the engineering level. In this part, we will cover some of aspects in numerical modeling. For example, the footing behavior with leaking pipe. And in part 3, we will scale down to the particles. And in this part, we will talk about the micromechanical modeling of unsaturated soil at the particle level. So now let's start with the part 1, the constitutive modeling at soil element level. So following the pioneering work done by Annan Zhou and his colleagues in 1990. It is very popular to employ section as a second constitutive variable in addition to the net stress or effective stress. So in general, these models assume compression modulus, this lambda S, compression modulus of unsaturated soil as a function of section. So compression modulus is usually involved in the hardening law for the most of the elastoplasticity models. So therefore, these models can be classified as a category that is section hardening models. Doesn't matter, we acknowledge the different models may use different assumptions. So we can see here two most popular options. So for example, some models adopt the compression modulus increase with suction, but some adopt just the opposite, it's decrease with the suction. So as long as the suction is employed as a second constitutive variable and control the hardening process, so we can view, they can be viewed as still in the straight section modeling framework. The straight section modeling framework, or let's say the section hardening models, achieved great success in ancestral soil modeling, in particular, how to interpret and modeling loading collapse behavior, but they still have some limitations. So for example, in general, they have the common problem in modeling a nonlinear compression curve, and constant sections and nonlinear collapse volume change and the constant sections. So no matter either option A or option B, you are going to adopt. These two limitations are existing. So we believe that section in the end, it is a stress variable which may not be suitable to be served as a state variable as well. So therefore, we assume the hardening of the unsaturated soil is more related to the degree of saturation, or let's say the effective degree of saturation, which is a function of degree of saturation, SE. So we assume the compression modulus is a function of effective degree of saturation rather than suction, and the volume change equation can be written like this, following the modified chemically model. So we involve the first coupling parameter A1, which can be used to couple the hydraulic variable SE to mechanical variable lambda. So now we changed the section hardening model to the saturation hardening model. So if we calculate the full derivative to the volume change equation, we can see the degree of saturation affects the volume change into two aspects. So on the one hand, SE affected the volume change by changing the compression modulus, and on the other hand, SE affects the volume change by changing the bonding capacity of meniscus. So here is experimental validation of the volume change equation we propose. At the constant section 100, 200, and 300 kilopascal, we can mimic the nonlinear compression curve. You can see here, nonlinear compression curve by using the proposed model. And this 1219 shows the comparison between the predicted specific volume and measured specific volume very well. So if we look into this volume change equation again, we can find the effective degree of saturation, SE, plays a very important role in this equation. So first, it constructs the Bishop's effective stress like this. So it is a component for the Bishop's effective stress. And it also serves as a state variable. It also serves as a state variable. And it is adopted as a hardening parameter as well. However, the effective degree of saturation itself is not a directly controllable variable. It is challenging to determine it from the controllable variable like section or net stress. So to solve this problem, we proposed an enhanced water retention equation which can consider nonlinear hysteresis for the cyclical drying and wetting. Considering the nonlinear hysteresis, we involve a new parameter B here, which is related to the liquid-solid contact angle. And this enhanced water retention equation can also consider the mechanical shift of the water retention curve and the constant suction. So to consider the mechanical shift, we introduce the second coupling parameter A2, which is able to couple the mechanical component volume change, volumetric strain with the degree of saturation. So due to the time limit, I skip all the details about this enhancement, but just to show you the modeling results. So these top two figures shows the scaling drying and the scaling wetting data and the modeled results, and the bottom two shows the cyclical drying, wetting, and the prediction. So we can see the comparison shows the model is able to mimic the nonlinear hysteresis of the water retention curve. The right two figures shows the observed mechanical shift of the water retention curve and our prediction. So we can see with the increase of the with the decrease of the void ratio, and the water retention curve is shifting upwards. And the prediction match the experimental results very well. Once we have the volume change equation and the saturation change equation, we can build up the full constitutive modeling following the modified chemical model or the Barcelona basic model. So we can derive the loading collapse surface, the yield surface for the unsaturated soil. This figure shows the yield surface for the unsaturated soil. And this table shows the parameters, what we use for the constitutive model. We need 5 mechanical parameters, which are the same with the MCC, and 5 hydraulic parameters like Van Gluten water retention curve, and 2 newly added coupling parameters, A1 and A2, right? And A1 and A2 can be easily calibrated by one constant suction compression test like this, all right? And now let's see the model capacity. These 4 figures shows about 20 isotropic loading and the soaking test at different initial density and soaking pressure. The blue curves are model predictions, and the predictions and the experimental results match each other very well, including the collapse segments. So we can see here several collapse segments. And these slides show 4 constant traxial compression tests and predictions. So for each test, suction and the degree of saturation are different. We can see here. And top two and the top figures shows the straight-strain relationship, and the middle ones shows the volume change, and the bottom one shows the saturation change. Again, we can see the model performance very well here. So as we mentioned previously, in the part 2, we will scale up to the engineering level. And in this part, we will cover some aspects in numerical modeling of unsaturated soil problems. For example, the footing behavior with the leaking pipe. And following the general way to build up the finite element program, we turn the proposed constitutive model into the constitutive matrix. So one point I would like to highlight here is, although we build up our model in terms of the Bishop's effective stress and the effective degree of saturation, the constitutive matrix for the elastic and the elastoplastic responses can be finally represented by using the raw variables like total stress, the total stress, strain, and water content, and the suction. We use the explicit integration for our model implementation. So to ensure the accuracy, we also involve the degree of saturation into explicit integration with the auto substamping control. So we can see here, we use this as a numerical example. So we use a 20 increment with 734 auto substamps. It can achieve better global error within much shorter computational time, compared with 20,000 fixed increments. This slide shows some validation example for our failure element code. The left figure shows the second column, test result, and our prediction. So the figure A here shows the section control, the section distribution change along with the depth with the time. And figure B here shows the isotropic loading and weighting test result, shows the outflow rate with the time. And this figure shows the isotropic loading and weighting test results and our simulations. So the good performance confirms the capacity of the constitutive model as well as the numerical implementation methods. So this is a numerical example showing the footing performance with a leaking pipe. So we can see this is a footing and this is a pipe with leakage. And this figure shows the simulated section profile change in the soil due to the pipe leaking. And this figure shows the simulated saturation profile change in the soil due to pipe leaking. So we can see for this point, for the leaking point, the degree of saturation getting to 100% along with the time. And this figure shows the simulated failure of the footing due to the pipe leaking. So we can see here, we can see the curve here. So for the near end to the leaking point, we can observe weighting collapse. But for the far end of the footing, we can observe the swelling of the ground. All right, now let's move to the part 3. In this part, we will scale down to the particles in ancestral soil, and in this part we will talk about the micromechanical modeling of ancestral soil at particle scale. So it is clear that the micro forces acting on the particle caused by water is highly related to the liquid solid interface. So for example here, liquid solid interface. So therefore, the first step for the micromechanical modeling of ancestral soil is to determine, is to have a quick liquid solid interface estimation that can be embedded into DEM. So here we employ a simple method for a quick liquid solid interface estimation. So for the overlapped caps, so for example, overlapped caps, or let's say the clustered interface, we use the hemisphere approximation, which is a simplified Young-Laplace equation. So for the isolated caps, we directly apply Young-Laplace equation. So to achieve this, we also developed a simple way to judge the interface, which should be classified as overlapped collapse and which should be classified isotropic isolated caps. So like this. So here, by using 22 particles, we compare the simulated interface obtained by using our quick estimation method and the pore morphology method for different sections. So we can see the performance is not bad, but more importantly, the quick estimation method is much faster than the traditional pore morphology method. So it will give us an opportunity to include it into the DEM simulation. Once we determine the liquid-solid interface for a particle, we will be able to calculate the Capri forces. So the Capri forces consist of two parts. They are the force determined by the liquid pressure Fs and the force determined by the interfacial tension F gamma. So Fs actually is related to the weighted area, this blue area, and F gamma is related to the solid gas liquid line, this red line. So, but we should know that the interface is maybe in a very complicated shape. It's not a regular shape. So the area of the interface and the length of the solid gas liquid line are therefore difficult to be estimated. So here we introduce the Fibonacci lattice points to divide the surface, into small but equal parts. This process is very similar to the meshing process in finite elements. So by this way, we will be able to calculate the value of Fs and F gamma for each particle. So the total force acting on a particle consists constant contact normal force Fn, contact shear force F tau, liquid pressure force Fs, and the tensile force at the solid gas liquid line F gamma. Once we identify the total force for each particle, we can make use of the commercial DEM solver to find the equilibrium. So for each stamp of the equilibrium, we need to update the liquid-solid interface and the related forces. So even we use the quick estimation method we proposed, it is still a very time-consuming process for this kind of simulation. So let's see the results. So we use a micromechanical model to simulate several desaturation tests and constant suction triaxial test with the different confining stress and the different sections. So we use 9,977 particles for the simulation, and their particle size range from 11.7 micrometer to 34.5 micrometer. So in the range of the silty clay. So we also calculate the effective stress parameter chi from our micromechanical model, which shows good match with the experimental results, better than the existing research from other pioneers. So the comparison here shows the capacity of our micromechanical model. So this figure shows the microscopic stress-strain relation behavior produced by the micromechanical model for the loose and dense sample with different confining stress and section. So we can see for the dense sample show the peak strength more distinct compared with the loose sample, and the sample with the high confining stress shows a high strength. And more importantly, we can find the sample with 40 kilopascal section shows the highest strength for all the groups. So this because at 40 kilopascal section, the product of section and the effective degree of saturation is the highest. So we pick up the strengths, including the critical strengths, peak strengths for each straight strain curve, and plot them together in the space of Q and average contact stress. So they show very good linearity, which indicates the average contact stress may be a good option for building up the constitutive model. So here now, let's see some microscope features of the ancestral soil. So these top three figures shows the estimated liquid solid interface, and the three figures in the middle show the Capri force distribution, and the bottom figure shows the angular distribution of the Capri forces. So the section for the first column is 20, the section for the second column is 50, and for the last column is 100. So we can see about 50 kilopascal section, we have the strongest Capri forces. And the left figure shows the frequency and the mean value of the Capri forces for different sections. We can which also show the increase in the Capri forces, increase of the Capri forces when we increase section from 20 kilopascal to 50 kilopascal. And this figure shows the liquid solid interface distribution, Capri force distribution, and angular distribution during the sharing. So we can see the axial strain for this figure actually is 0, 2%, that is the peak strength, and 20%, that is the critical state. So we can observe the Capri forces turn from the isotropic distribution to anisotropic distribution during the sharing. And the plot of frequency and the mean value also show the increase of the mean Capri forces, which means the Capri network contributes more and more to resist the external sharing. And this figure shows the variation of the contact force network for 0 section. This is for 0 section. This is for 40 kilopascal section. So we can see the contact force.
You have 2 minutes.
Yeah, that will be enough. This is the last slide. And we can see the contact force network at 40 kilopascal is much stronger than that at 0 section. All right. And from the frequency and mean value plot, we can also identify at the entire sharing stage, the mean contact force with 400 kilopascal section is much higher than the mean contact force at the 0 section. So that's why we observe the straight strain curve of 40 kilopascal section is much higher than the others. Right. So now let's move to some concluding remarks. Let's make it simple. So the first point, the Bishop effective stress and the effective degree of saturation are adopted as the basic constitutive variable. And the hydraulic hysteresis and the fully coupled hydromechanical interaction can be considered. And the current model is more suitable for the silty soil. It is still very challenging to model the clayey soil over a large section range. And this framework cannot be used for the unsaturated expansive soil either. And the constitutive model has been implemented into the fan element codes. And the developed in-house fan element codes can be used for 1D, for example, the soil column, and the 2D, let's say the footing analysis. But the current fan element is still hard to be applied to the real case analysis. So for example, 3D multi-soil layers and natural environment. The micromechanical model has been built to bridge the micromechanical characteristics and the micromechanical observations. But due to a few assumptions, the comparison between the results from the micromechanical model and the macromechanical observation still remain in mechanism. So it is still hard to compare the results directly with the ancestral soil test results. All right. So all in all, in unsaturated soil research, we still have a long way to go. All right. So this is the last slides with some key references. So for more details, they can be found in publications listed here. May be useful for the postgraduates. So thank you very much for sharing your time with me in this morning. All right, thank you.
Okay, thank you, Professor Zhang. Very excellent presentation. Due to time limitation, I'm sorry we have not more time for question and discussion. If you have some questions, please send an email to Professor Zhou, and